So today's last bit is on adding angular momentum, so you can do those last one or two questions. And as I mentioned, it is overwhelmingly difficult. It looks overwhelmingly difficult until you learn to read a Clebsch-Gordan table, which I passed those around, so all of you have a Clebsch-Gordan table, right? So I'm going to show you how to read that, and it's going to make everything way easier. All right, so let me just remind you where we did. So we started adding two spins, and I didn't say what the final spin. Let's say that one spin up and the other one spin up or spin down. But this was a simplification, because what we really want to do is J is equal to L plus S. Now in this case, when you have an excited helium atom, there is no L. So really we're doing S, S1 plus S2. So again, there was no L, but there wasn't another S. And so the total J is, the total angular momentum in this case is just the total S. So S is J in the case of all S orbitals, because again, there's no L to be added to begin with. It's still all exactly the same. And really, when I do that, that's actually kind of stupid. What you really have to do is you have to create a basis set, up, 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 down, down. Your basis set needs to be everything you can think of. Okay, so there's 4 basis vectors, and I represented them like this. So there's a bra, here's a ket, dot, 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 minus, minus, dot, 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 minus, minus. And S squared, the S squared matrix, ends up being 0, 1, 1, 0, 0. Ended up looking like this. Okay, now let me note that, of course, one problem with all this is that you can't really determine spin. You have to determine spin squared, and that's where you run into this horrible. None of this is hard until you do this. Until you run into this damn dot product. So what you end up doing is, now again, I've covered all this. So again, we're adding angular momentum. Don't forget there's a dot product. You run into problems with Sx and Sy. Again, we've covered all this. You use ladder operators. Once you have ladder operators, you can then solve this matrix in this basis set. That's what the ladder operators do. And when you have this matrix, you can then figure out that S is 0 or 1, which is singlet or triplet. Okay, and then you can also ask for the Eigen Functions, and you learn that you have the singlet is going to be, sorry, I should just 1/2, put the square root over the whole thing, and that would be, so I'm writing this in terms of configurations, it'd be minus, my handwriting just disappeared. So, what's kind of funky about this is when you look at your basis set, see, the thing is you have 2 configurations. Two configurations, right? Up, down, down, up, down, down, up. And so I can see that both the problem is that it looks like the spin cancels on both of them, right? Both of them have an up and a down, so therefore they have S0, but there can only be one singlet state. So that's crazy, right? But the answer is that remember that this representation is what you understand. It's not what nature understands. It's not what a Hamiltonian understands. So these are not eigenstates of the Hamiltonian, and when you do it properly, you find that it's a linear combination of up, down, and down, up. And oddly, they kind of subtract. I kind of would have thought they would have added. But the triplet is obviously up, up, down, down. And then, of course, it ends up, I mean, just the mathematics decided that it was the same configuration but added together. And that's just what it wants. I mean, I don't know that I can do a better job describing it than just to say this is just what you got. It's hard enough to set this stuff up. Okay, so we covered that. Then technically, so that's an overly simple one, and you know about singlets and triplets already. So then, instead of a system of just an S and another S, instead I went from having one S and one L unit of angular momentum by doing this problem. By doing a 2p1 state. So for a 2p1 configuration, I've got one electron, 1, 2, 3. And again, it's kind of stupid simple. To make this work, you want to track this stuff. So m sub L, 1, 0, minus 1 question. 1, 0, minus 1. M sub S is 1/2, 1/2, 1/2, minus 1/2, minus 1/2, minus 1/2. Okay, so what we wanted to do here is add angular momentum, but we're not going to be doing any more matrices. I'm going to show you how to figure out the term symbol. This one, you can kind of just stare at it and figure it out. When it comes to this one, you absolutely cannot. So just like I could look at these and know whether I had singlets or triplets and do a more complicated process, I'm kind of doing the same thing here. I can look at this and figure out the term symbol, but when the rubber hits the road, I'm going to have to do a more complicated process. And that's how I'm trying to walk you through this. Okay, remember a term symbol is going to not only uniquely identify an electron configuration, we're probably going to do, this is going to end up being, we're going to identify states, kind of like getting the eigenvalues first, and those will be eigenvalues of the Hamiltonian, and then we'll get Eigen Functions second. It's kind of like that. Actually, it's almost exactly like that. And what we're doing here, I mean, we're doing this here as well, is that you're going from this basis, this summation is going to go from the basis of L, M sub L, S, M sub S, into J, M sub J, where J is L plus S, S and L. Right? Sorry, it's usually written L and S. L is considered dominant over S. Anyway, that actually is meaningless. They're different things. No, I drew that the right way. Okay, and again, J is L plus S. Okay. All right, now again, I want to emphasize that there is a rigorous procedure to do this, which you're going to see. But in this case, you can kind of just figure it out. So I wanted to show you two things that this makes sense, but when it becomes cross-eyed, then just follow the procedure and you'll figure it out. Okay, in this case, the reason that you can kind of figure this out is because you only have one electron, and so your spin, right, there's only one spin, right? 1/2, is that right? Right, there's only one spin, 1/2. Wait, huh? What, was there one or two? There's only one spin. You're looking at M sub S, I'm talking about S. S is 1/2. An electron has a spin of 1/2, but it could be, there's an M sub S of plus or minus, because it can be up or down. When I say what is the S, I'm talking about that S. the 1/2. It's only 1/2. This can be up or down, but I'm not talking about that. So I tricked you. Saw that? That makes me feel good because I have so little in my life. Anyway, that's another problem. Okay, so I can, because there's only one electron and the spin is 1/2, I know immediately that I've got a multiplicity of 2, which is called a doublet. And in all honesty, with only one electron and everything's in a p orbital, then L has to be 1, so it has to be p. So this one is just kind of too simple. Okay, now for the J's. Now this is where I ended last time, and I didn't really explain it, but it has to do. Now you're going to add L and S. So J is L plus S, and this is called a Russell. I think that's 2L Saunders. Russell-Saunders coupling scheme. Now it's just a matter of vector addition. I'll show you some. I'll do some vector addition. But the way it works, and this is for light elements. Okay, if you have heavy elements with high spin orbit coupling, you do a procedure called JJ coupling. Okay, the way this works is, it's actually really simple. L plus S minus 1, to L minus S, absolute value of L minus S. Okay, so that's how it works. And again, it's all about vector addition, and vectors can only be positive, right? There's no such thing as a negative link to a vector. Here, let me actually just go ahead and show you. So that's like, here that's L, and here's S. And so the result is J. And now, of course, recall, I didn't draw that very well. Recall, of course, that the way we represent angular momentum are on these cones. So here's the J vector. X, Y, all that jazz, remember all that? Okay, and so the total vector is J, and then what's this value right there? The projection on the Z is what? Huh? What was it ever? Okay, for S is 1/2, it can be plus half or minus half. Why is that? Plus or minus a half on what axis? No. Okay, what is our fundamental basis set for spin? Z. Okay, so this would be the component in the which axis, which is clearly drawn. Z axis. Right. So that's M sub J. Right, S is 1/2, so the M sub S's are plus or minus a half, which is the projection onto the Z axis. So the total angular momentum, still being angular momentum, does the exact same thing. So, and so when you figure out what L is, so let's figure out what J is. Sorry, J would be L, okay, that's 1, S is 1/2. Okay, so that's 3/2. Now, it turns out there's another one. So, so 1 plus a half, 3/2. 1 plus a half minus 1 is 1/2. Okay, but they can't, and you don't go further. You can't be negative. Sorry, now that's actually an additional term symbol. Okay, so something with a 2p1 configuration has 2 potential term symbols. Now, if we have 6 states, we better end in 6 states, and recall that just like a PZ orbital, a p orbital has a px and a py and a pz. Remember that for L is equal to L, M sub L is equal to L minus L plus 1 plus L. Okay, so therefore a 2p 3/2 has additional states, which are m sub j is minus 3 halves, minus 1 half, 1 half, and 3 halves. All right, so you see that? So again, in the same way that you can have 2L plus 1, when you learned about the hydrogen atom, and you learned about P's and D's and F's, there are 2L plus 1 of them, right? So there's 3 P's, 5 D's, 7 F functions, and then I don't think anyone has a G. So when you have a 2P 3 halves, just like, yeah, so you end up with M sub J's, right? That's how you do the M sub J. So for 2P 1 half, you're going to end up with M sub J is, of course, minus 1 half and 1 half. Now, the point of this is that if we had 6 basis functions, then we need 6 linear combinations. 1, 2, 3, 4, 5, 6. Okay, so, and the reason we made linear combinations is because we added the angular momentum into a total angular momentum representation, which would be how nature understands this atom. Confusing to us, but correct to nature, because what we can do is we can do spectroscopy on this atom, and guess what? We're going to see 2 different states, right? We're going to see an absorption between a ground state and an excited state, and I can tell you that it'll actually be, this state will be lower than that state, so that's actually due to spin orbit coupling. And I'm not going to say too much about that, but it turns out that there's these rules for writing term symbols. So we're covering how to write term symbols, but there's rules for their energetic ordering. This one will be lower than that one because it has a lower J and a half-filled, less than a half-filled orbitals. And so I'm not gonna harp on that. I just want you to know that those rules exist. They're called Hund's rules. They're very fundamental to spectroscopy because spectroscopy on an atom is where you begin spectroscopy. You're not going to get simpler than that. Even for something as simple as a 1p state, you need to learn how to write the term symbols. Then you learn how to do the energetic ordering. Those are Hund's rules. So I'm not going to cover them. I just want you to know they exist. But you learn that like the 2p 1 half has lower energy than the 2p 3 halves. Now again, that's not a big deal because people don't really do spectroscopy on atoms anymore. Some people will tell you that's a shame, but I think we put every atom in every spectrometer you ever could, including ions, right? So, okay, so there's that. Now let's do the wave functions. So it's like I kind of got the eigenvalues, right? Because those are related to the energy. So what are the wave functions? Okay, to do that part, recall last time that I had to create a matrix, the S-squared matrix, which was relevant to the problem, and then get the eigenvalues, the eigenfunctions. In the Clebsch-Gordan table, which I handed to you, these geezers, they already figured it all out. You just have to learn how to read it. That's why I'm telling you, this is actually really easy. When I show you the algorithm for calculating term symbols, you have those, and then you look at the Clebsch-Gordan table to get the wave functions. That's all you're ever going to do. And just recall that, again, this is a combination of atomic orbitals, which you know how to do since high school, but you're putting it in the form that Mother Nature understands, which is Eigen Functions of the Hamiltonian. So, you know, these could be like bonds, right? This could be like a benzene molecule, and these are bonds. And the result, put these into a Hamiltonian, now come eigenvectors, those are your molecular orbitals. So this is kind of a big picture thing. All right, when it comes to adding angular momentum for Clebsch-Gordan, spell funny. Anyways. Okay, so we're going to do that for this one. And what you're looking for is the L equals 1, S equals 1 half table. And I forgot which one that it's one of the smaller ones. It's a little hard to find. That table is pretty dense. But if you find it, it's one of the smaller ones. It's actually the second from the top. Second from the top left. 1x 1/2, right? So that's 1/1/2. So you're going to notice that at the top you have this. You have a box. You got 3 halves, 3 halves. You got another bigger box. We're only going to do a few of these. 3 halves, 1 half, 1 half, 1 half, 1 minus. Maybe I'll go ahead and do them all. Something like that.
That's -1/3, the last one. The bottom right of the middle box.
Yeah. It's actually in my notes. I have to point that out. Not the end of the world if I got it wrong and you see what I'm about to do. So these are never difficult. These are not difficult at all. It's just that there's a whole ton of numbers and you just got to keep it straight what's what. Okay, so here's the damn thing. So what in God's name do you do with it? Now again, I'm telling you, the difficulty of figuring out what the configurations, what are the wave functions for these is actually in here. Here's how you do it. On the left are the bases. Now remember, these are going to be the ML and MS. Remember how I told you that we abbreviate the configurations that you know how to do. We abbreviate these as M sub L, M sub S. That's on the left, and on top are what you actually need to understand the Hamiltonian, which is the J, M sub J. That's what you actually want. Okay, so look on top, look at what you want. On the left tells you what you have to work with, and the interior of the box tells you how to construct it. Now that's the big picture. If you can remember that, you can actually kind of just figure it out even if you forget. Okay, so now let's go back over here and remember that we want a 2p 3 halves and a 2p 1 half. We actually have 5 p's and 2 of those. So, okay, so I'm looking for a, now of the 2p 3 halves, we technically have a 3 halves, 2p 3 halves, 1 half, 2p 3 halves, minus 1 half. Okay, so we have those. Let's see if we can find them. All right, now, who sees 3 halves, 3 halves?
First one.
Yes, the top one. Yeah, sorry, I didn't write them consistently, did I? I kind of put them on top of each. Okay, 3 halves, 3 halves. Now remember, this is your basis. Okay, so where? Oh, damn it! I shouldn't have erased that. I was really stupid. 1, 2, 3, 1. Okay. 1, 0, minus 1, 1, 0, minus 1. Okay, so where is 1 1 half? The very first one. Okay, so this guy is the wave function corresponding to a 2p 2p0 psi of anyway, it's just this. It's just this. Okay, so it's yeah. Actually, I had written this. Yeah, the wave function would actually be r e to the minus r over 2a naught sine theta e to b by b. Right, so 2p radial wave function, and then this is the p0. This is the p0 spherical harmonic. No, p plus 1. It's the p plus 1 spherical harmonic, right? P0 would be just cosine with that's not there. So that's the Amsabel plus 1. Okay, anyway. So my point being is that this table finds you the configurations. Now this one was kind of easy, so let's do a harder one. I want to make sure I got my notes. Okay, let's do 3/2, 1/2. So where's that? Yeah, it's the second one. Okay, so let's do this one. Now what it says is, it is square root of 3 times a configuration, these are all square rooted by the way, of 1 minus 1/2. So where's 1 minus 1/2? Yeah, exactly, fourth one. Okay, plus square root of 2/3 in a configuration of 0, 1/2. Yeah, there you go. Not particularly hard, is it? Yeah, there you go. It's like the most complicated thing ever, and it's being done very easily for us. Okay, let's do this thing. Okay, now we got a much worse one. Now we got something that's actually hideous. How do we deal with this? Okay, so what we're going to do is first create the term symbols, and then you can look up the wave functions on the Clebsch Gordan table. Now this time I'm going to actually show you something that is this is like the last new thing I'm going to show you, but this is anyway, so you got to get the term symbols, right? Okay, now, before I do, I want to get a feel for this thing. I want to get a feel for it. I'm not going to just try to figure out the term symbols like I did before. I'm going to just look at it and try to get a feel for what I should get. Now, for one, I can look at all these, and I can see spin up and spin up. So these look like triplets. And the rest of these are spin up, spin down. So these all look like singlets. Okay, so I'm making headway. I'm seeing what's a singlet, what's a triplet. Okay, so there's that. Now, I'm looking at this one right here. And remember how you draw little cones? Okay, now this one has here's the z-axis. And it has, on the z-axis, it has a projection of 2 h bar, this one, right? Because +1, +1. All right, that means it's angular, that means that it's, J has got, if this is the JZ, that's the JZ component, then the J has got to be, what? Is it S, which would have no link? P or D? So remember, an S cannot have a projection onto Z because there's no spin at all, with no angular momentum. Sorry, it should say angular momentum. A P can either be 1, 0, or -1. So it's a D state. Okay, so I can look at this and see that it looks like I have a singlet T. All right, so I'm getting a feel for this. Anyway, that's not how you do this. I just want to point out that you can look at this and start to make sense of it. Because these 2 electrons in this that have this v component of angular momentum, they have a lot of it. And the only way you can have a lot of a projection onto an axis is if your total vector is large as well. So anyway, here's how you do this. First thing I'm going to do is I'm going to figure out what my spins are. And my spins, notice that I need to add, remember how I told you how you're going to have to add 4 things at one point? That would be my final example. Well, this is it. You're going to have to add 2 spins, and then you're going to have to add 2 angular momentums, 2 electrons. Each electron has an L and an S. So each one has 2, and there's 2 of them, so there's 4. There's 4 things that have to be added. Okay, so what I'm going to do is S is going to be S1 plus S2, dot, 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 to S1 minus S2. So remember how I just did that? L is going to be L1 plus L2, dot, 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 up to a maximum value of L1 minus L2. Okay, so this is going to be 1/2 plus 1/2, that's 1, and 1/2 minus 1/2 is 0. Look at that, I got singlets and triplets. Okay, let's look at this thing. So the angular momentum of a p state is 1, and there's 2 electrons in a p state, so that's 2. And then by the rules we developed, it's 2 minus 1 to a maximum of 1 minus 1, which is 0. Okay, so triplet, singlet, P, D, S state. So I'm looking for 6 states. What did I say?
DDS.
Oh, sorry, yeah, D and P and S. Okay. So that's L and that's 2S plus 1. Yes, all right. Now here's the trick. Here's how you do this. And I think this is a Wikipedia. This is from Wikipedia, so I'll send that link to you. This is the best way I've ever seen to do this. What you do is you write the M sub L's on the left side, and you write the M sub S's on top. Okay, so, and then you count the number of states that have those values. Okay, so in terms of 0, 0 at the center, 1, 2, there's 3 of them. See that? See how I did that? Again, you know, a child can add up these numbers. Now we make this table, and we're going to add up how many we have. Okay, let's see. What about 1, 1? Here, it's only 1. Okay, let's look up 1, 0. 1, 2. Okay, how about 2, 0? There's 1. Well, I know what they are already, so. No, I'm going to cheat. Okay. Okay, total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 states? Guess what? There's 15 states. Again, it all adds up. Okay, now again, remember the goal of this is to figure out the term symbols, and then you can use Clebsch Gordan to get your wave functions. Okay, now the way to do this is, I think this is actually kind of fun. I hope you find it kind of fun, but it's not. It's an algorithm, but it's not like it's like an algorithm, like a crossword's an algorithm. Okay, now I have a clue that I'm looking for a D state. A D state is going to have, like all D states, there's 5 of them, right? Px squared, x squared minus y squared, z squared, dxy, yz, and zy, right? So there's 5 D states. Now when I look at this, I see 1, 2, 3, 4, 5. So I see the potential to create 1 D state. So let's start bit by bit. Let's say that we have a D state. And what I'm going to do is I'm going to take out the center one. So I've now taken this box and added it up into 2. Okay. So in other words, I've taken a box out of the center and put it over here. It's got to be a D state because there's 5 M sub L's. Only a D state can have 5 M sub L states. P states, and it looks like I got a P state. See, I can kind of forget. See in here, look at this. You see why I have a P state? Because I've got M sub L's of 3. So therefore there's P states in here. So now I'm going to start taking more boxes out. Okay, now if we go back here, this looks to me like a singlet D state. Now the reason is that if it's a triplet, I should have +1 and -1 M sub S components, right? So a triplet, there's 3 of them. That's why 3. So there should be 1, 2, 3, but there's only a center M sub S of 0. That says to me that this is a 2S plus 1. It is a singlet D. Okay. So now I've pretty much identified. I've done pretty good. I've identified 5 states. 5 out of the 15. I have 10 more. Okay. Now let's take out the central box. It looks like there's 1, 1, 1, 1, 1, 1, 1, 1, 1. Let's see, what does that do for us? Let's take out 9. Okay, let's take out 9. All right, now, this looks like this definitely looks like a P state because only a P could have 3. P's have 3 states: PX's, PY's, and PZ's. So I'm going to say that this is a P state. Triplet or singlet? Now, triplets have how many M sub S states? How many states should a triplet have? What? Okay, why is it called a triplet? Yeah, it's like 2S plus 1. So this is a triplet. Remember that these are the sub, there's the long vector and then the sub vector, right? The projection onto Z. This one's spin is projecting onto 3, is projecting onto the Z axis with +0 and -1. Only a triplet does that. So this is a triplet P. Okay, now we're left with a one state that has no spin and no momentum. That's an S state. It's an S0 state. Sorry, S1. Sorry, 2S plus 1. S is 0, 2S plus 1 is 1. So singlet S. Okay, last bit. Okay, let's figure out what the J's are. Okay, so singlet D. Okay, so 2S plus 1 is 2S is that right? No, let me check my notes. No, sorry. S is 0. All right, so remember, J is L plus S. Okay. L is 2, S is 0. So this is 2. Okay, that's great. Now, remember that now we've got to consider how many states are there. All right, so the subpopulation is, if this is J is 2, then M sub J can be 2, 1, 0, and this is awful, -1, and -2. Okay, so this term symbol encompasses 5 states. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, P states. Okay, so L plus S, 1 plus 1 is 2. Okay, then the other combination is is L minus S, and that would be that'd be 0. So that means that we have 3 of these. All right, so again, remember that this comes with this Russell-Saunders scheme that J is L plus S, L plus S minus 1, dot, 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 L minus S. Okay. 1 plus 1 is 2. The maximum is 1 minus 1 is 0, so there's a 1 in between. Okay. 5 of these, right? 2, 1, 0, minus 1, minus 2, 5. 3 of these, 1, 0, minus 1, and 1 of these. 5, 3, 1, 9. Okay, there's only one state. 9, 10, 5, 15. 15 states. So, so there you go. Let's see, the last bit I want to mention is on wave functions. So this is the algorithm by which you figure out your term symbol. Again, when you do it on your homework, if you work through it, it really is relatively straightforward, and it's kind of a little bit on the fun side. Let's see, if you look at, okay, for the wave functions, okay, so let's do 3p state. And there's, so what you would look for is it's written as L and, well, it's the coupling of two angular momentum. There's L and S. Now, in this case, L is 1, S is 1. So you're looking for the one by one table. All right, do you see the 1 by 1 table?
Third down.
Yeah, third down, fourth down. Anyway, guess how many entries there are? All right, add them up. One, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 entries. How many 3p states are there? 9. Right, there's 9 of them. Okay. Now the last thing I want to point out is we had 2, 1. Okay, I won't draw the rest of it. Okay, so now we're doing 3p. Okay, now remember these are your basis functions and these are what you want. So let's say we're looking for a 3p2, and of those 3p2s, there's a 2, 1, 0, minus 1, minus 2. Okay, so let's do 3p21. Let's do 3p21. Okay, where is that? Right here, right? 3p21. What you're going to do is take the square root of 1/2 of the configuration with, that's 1, 0, and that happens to be 1, 0 happens to be this one. If you look at the 15, right? So 1, 0 has to be this, plus 1 with the square root of 2. Now notice that the next one is 0, 1. Is, wait, no, sorry, is that, which one is that? Sorry, I've got, no, sorry, 0, 0, 1. Sorry, 0, 0, 1 is easy. 0, 1 is this one. Okay, then you've got then you got 1, 0. Okay, 1, 0. Now, do you see a problem if you look at the table? I didn't write it down for you. There's actually 2 of them. So I'm going to end with this. So if you look at your configuration, you have a bit of a problem with constructing this state. This guy you're cool with. That's right here. Sorry, why did I do that? That's right here. There's only one of them. Okay, but 1, 0, how many of them were there? There are 2 of them. Which one is it? Just pick one? Okay, now here's the trick. It turns out that, remember how I added spin states in that table? But I didn't do it properly, right? If in this case, look at this. This is up, down, down, up. You ran into that before, right? Those are is that a single or triplet? It's both. Remember, all right, so we're doing a triplet state. So what it really is this. So the answer is, by the way, is that I did not properly add spin to begin with. Again, remember how I had to add up 4 things? I only did 2 of them. Spin has to be added in the following way. Okay, since this is a triplet, guess what? It ends up being a linear combination of these. Up, down. If it's a triplet, it's the sum. See what I mean? It's kind of nightmarish, but when you have these guys, had I added them up before I did any of this mess, I would have identified in here a combination of plus, which is a triplet, or I would have subtracted them, which would have been a singlet. And that singlet would have gone into the D state. That's one of the singlet Ds. The triplet, the one where you add them, is a triplet, so it belongs to the triplet D. And specifically that one. So anyway, look, I know that was kind of confusing, but I believe that's the problem you have on your homework. So that's how you're going to work through it. In fact, I think I allude to that